Chapter 1. So, what are we going to learn? What will you learn in this Intro to Chemistry course? Well, let's think of kind of a real-life example. When you get a headache, when you get some kind of an injury, usually most people take aspirin or Advil or ibuprofen, some kind of a over-the-counter medicine to help inflammation. So how does that really help? What does the aspirin do to actually relieve the headache or the pain that you have? Well, when you have a headache or you get an injury of some sort, what happens in your body is prostaglandins form. They're produced and they're the ones that cause that inflammation and pain to happen. So when you take aspirin, it blocks more production of those prostaglandins to form, which then alleviates some of that inflammation and that pain. So specifically in the medical field, chemistry comes very, very into play, and actually all around the world. In medical fields, chemists develop new treatments for diabetes, genetic defects, cancer, AIDS, and many other diseases. And the reason I like chemistry so much is just how much it applies to any kind of job that we want, based off of the skills that you use to study the material. And what I mean by that is for nurses, dietitians, forensic laboratory scientists, chemistry plays a central role because they have to understand the problem that's happening. Then when they see a problem and understand what's happening, they have to assess it. What are possible solutions to fix this? And then make really important decisions. Now, this can be medical field related. This could be any field related. It's always looking at a problem, coming up with how to fix it, understanding it, applying it, and then presenting the solutions and explaining them, really understanding what's happening. So chemistry is the study of the composition, properties, and interactions of matter. So that's what we'll be looking at in this class. Now, we'll talk more of matter a little bit later in a couple different chapters, but for now, very generic definition of matter is anything that has space, that occupies space and has mass. So the textbook that you're using for this class, or a pen that you're writing with, or the screen you're looking at to watch this stuff, that is matter. Anything that takes up space and it has mass. Now, matter itself is composed of tiny little particles called atoms. Now, we don't see these atoms. These are really, really, really small. Atoms come together to then form something called molecules or compounds. Now think of a molecule, water. Water is made up of 2 hydrogen atoms, and an oxygen atom. Now when you drink a glass of water, you don't have just one water molecule. Enough of the molecules come together to eventually be big enough so that we can see it. Now the scientific approach, the way that we go about chemistry experiments or chemistry in general. The first thing that happens is there's some kind of an observation. You're day-to-day, or you notice something in lab and you make an observation about something about nature and you ask yourself a question about what you observe. Now, I always like to use a very generic example of something being allergy related. So suppose you visit a friend at her home and soon after your eyes start to itch and you begin to sneeze. So you immediately observe that and you ask yourself, why am I sneezing? What's going on? You see that your friend has a new cat. A hypothesis is a temporary explanation for an observation. So you went to your friend's house, you began to sneeze, you noticed that there was a cat there, so then you're making all these observations and you come up with a possible explanation for that observation. You say that you're allergic to cats based off of your observation. You must be, that's why you're sneezing. So you form your hypothesis based off of what you notice. You are allergic to cats. Now, in order to test a hypothesis, you have to actually do some experiments, because just because you're saying this is going to happen or this is what the case is, doesn't mean it's true. You have to have some backup for that. So experiments are controlled procedures designed to test whether a hypothesis is true or false. So you test your hypothesis by leaving your friend's home and observing whether you continue to sneeze. You test your hypothesis further by visiting another friend who also has a cat, and you sneeze again. But once you left, you began to sneeze more, and no cats were around. So these are the different experimentations that you did to try to prove your hypothesis. When the results of the experiments are analyzed, a conclusion is made as to whether the hypothesis is true or false. You then come to the conclusion that you have a cold. So when you are looking at the scientific approach, you start with making an observation. You notice something in nature, in your surroundings, and you ask yourself a question about what you're observing. Then you formulate some kind of an explanation. That's your hypothesis, trying to answer what your question is. Now, again, you can't just say this is true because you don't have any backup, no data, no results. So then you form some experiments to test what you're predicting your hypothesis is. When you have your experiments, you have some data to look at and you analyze the results. When your hypothesis is correct, then you can report your results. If it is incorrect, then you try again, meaning, all right, same observation, same question, what could be another possible explanation for this? So at a popular restaurant where Chang is the head chef, identify each of the following as an observation, a hypothesis, an experiment, or a conclusion. Chang determined that sales of the house salad had dropped. So basically, the chef realized that the sales of the house had dropped. Is this an observation, a hypothesis, an experiment, or a conclusion? I would say this is an observation because he noticed this. Chang decided that the house salad needed a new dressing. So he's making a decision about what to do. So because the sales have dropped, he decided, okay, I need to make a new dressing. So that would be a hypothesis. In a taste test, Chang prepared 4 bowls of lettuce, each with a new dressing. So now we're testing in there. Different things are being done. So this is an experiment. Something I'd like to say and point out right away is throughout some of these practice, you can always, and I encourage you to pause the video actually and try it on your own first before listening to me going over the questions. Identify each of the following as an observation, a hypothesis, an experiment, or a conclusion. So let's do this a little different of a way, this time going through all of them at once and then answering. 1 hour after drinking a glass of regular milk, Jim experiences stomach cramps. Jim thinks he may be lactose intolerant. Jim drinks a glass of lactose-free milk and does not have any stomach cramps. Jim drinks a glass of regular milk to which he has added lactase, an enzyme that breaks down lactose, and has no stomach cramps. So what are we thinking? A, 1 hour after drinking a glass of regular milk, Jim experiences stomach cramps. Is this an observation, a hypothesis, experiment, or conclusion? This is something he noticed, so I'm going to say this is an observation. Jim thinks he may be lactose intolerant. So he observed that he got stomach cramps after drinking milk. He's saying he's lactose intolerant, so that's a possible answer. This is a hypothesis. Jim then drinks a glass of lactose-free milk and does not have any stomach cramps. So what would that be? That would be an experiment because he's testing whether or not he's lactose intolerant. Jim drinks a glass of regular milk to which he added lactase, an enzyme that breaks down lactose, and has no stomach cramps. This is also testing his theory, experiment. So a little bit further on the scientific method. So sometimes a number of similar observations lead to the development of a scientific law. If enough observations of the same thing are being made, scientists can make a big, bold statement about that observation called a scientific law. A brief statement that summarized past observation and predicts future ones. Based on his observation of combustion, scientist Lavoisier developed the law of conservation of mass. Due to many observations, he was able to come up with this law that says in a chemical reaction, matter is neither created nor destroyed, and that's something that we'll look into a lot of detail in this class. One or more well-established hypotheses may form basis for a theory. So something really important I want to point out, a scientific law comes from many observations. A scientific theory comes from well-established hypotheses. Well-established hypotheses means that the hypotheses were proven to be true, so they have those experimental data to back them up. So theories provide a broader and deeper explanation for observations and laws. John Dalton's atomic theory explained the law of conservation of mass as well as other laws and observations by proposing that all matter was composed of small, indestructible particles called atoms. Scientific theories are also usually called modules. Which statement is a scientific theory? When the pressure on a sample of oxygen gas is increased 10%, the volume of the gas decreases by 10%. The volume, this shouldn't be a question mark, this should probably just be a period here. The volume of a gas is inversely proportional to its pressure. A gas is composed of small particles in constant motion. A gas sample has a mass of 15.8 grams and a volume of 10.5 liters. Now, remember, a scientific theory comes from well-established hypotheses, not observation. So which one would be more of a hypothesis rather than an observation in these statements? Now, what I would like you to do, I'm actually not going to answer this. I would like you to answer this on your own, and you'll submit the answer at the end with your summary of the lecture study for the day. Analyzing and interpreting data. So this is something that's really crucial in chemistry because you do a lot of experiments and you look at a lot of different numbers, and the way that we look at the numbers and analyze them is important to understanding what's going on. So suppose you're an early chemist trying to understand the composition of water. You know that water, H2O, is made up of hydrogen, 2 hydrogens, right? Because there's a 2 here, plus an oxygen. You do several experiments in which you decompose different samples of water into hydrogen and oxygen, and you get the following results. So you just take water and you take 3 different masses, so A, B, and C. You see 20 grams of water, 50, and 100. And then you decompose this water into the hydrogen and oxygen and get some results. Now, do you notice any patterns in the data? So just take a moment. I encourage you to pause the video and look at this data table and just write down a couple little notes of any patterns that you notice. Some may be more obvious, some may be not. Okay, so hopefully you paused it. Let's look. Something that I noticed is the sum of the masses of oxygen and hydrogen always sums to the mass of the water sample. So the 17.8 plus 2.2 gives you your 20. The 44.4 plus 5.6 gives you your 50. The 88.9 plus 11.1 gives the 100. So whatever you got for hydrogen and oxygen sums back up to the starting mass of water that you had before you decomposed it. The ratio of the masses of oxygen and hydrogen is the same for each sample. Now, how did I determine that? Sorry, I keep going back and forth. So the ratio of the masses is the same for each. So 17.8, 2.2, 44.4, 5.6, 88.9, 11.1. These are all the same ratios. It doesn't matter how much the number is. It doesn't matter the amount of water that you have. It's always going to produce the same ratio of oxygen and hydrogen. Seeing patterns in data is a creative process that requires you to not just merely tabulate laboratory measurements, but to see relationships that may not be so obvious all the time. Now, another really important thing is looking at graphs, not only making them, but if you're given a graph, understanding kind of what is being said, what message it's trying to tell you. So data is often visualized using graphs or images, and scientists must constantly analyze and interpret graphs. So here we have this figure, atmospheric carbon dioxide levels from 1860 to present time. What was the concentration of carbon dioxide in 1960? So let's see, my year is on my x-axis. This is my x-axis. And my carbon dioxide concentration in parts per million is my y-axis. So I'm asked, what was the concentration of carbon dioxide in 1960? Okay, so I'm looking at 1960. I first want to understand all the markings. So I go from 1860 to 1900. That's a difference of 40 years. Well, that means this could be 1880 because that's 20 and then 20. Then this could be 1920, this could be 1960, this could be 2000. Okay, so then I just determined where my 1960 is going to be right here, and I want to know the concentration of carbon dioxide. So then I'm going to draw a little line and come up. It's right here in this dot. So then I have to figure out what that concentration is going to be. So it's not exactly on the line. You can make yourself a little dashed line. So let's understand the y-axis. 300 to 320 is a difference of 20. There's a little dash in the middle, so that means I have 310 here because it's right in the middle between 300 and 320. So my concentration is somewhere between 310 and 320. It's a little closer to the 320. Now again, this is interpreting. But when you make yourself little markings like that and write on your graph, you can be more accurate. Because if you had just said 310 or 320, you would not be very accurate because it's definitely in between the two numbers. So I'm going to say I have around 318 parts per million. So important to always include your units. What was the concentration in 2000? How much did the concentration increase between 1960 and 2000? And what is the average rate of increase over this time? So what I want you to do is I want you to answer these questions on your own, and you'll submit this with your kind of end of the day review. For the average rate increase, you're looking at an average. So you're looking at the difference of your final minus your initial when you're looking at an average over time. So basically, what is the difference from where your concentrations, parts per million, at 2020 minus the parts per million at 1860 over the difference in the years, 2020 minus 1860. That's how you're looking at a rate, the amount of concentration change per time. So you're looking at the difference of the concentration of 2020 to 1860, and then you'll answer that. So always kind of picking apart a different graph and looking at the units that you have. So last but not least for this short little chapter is learning chemistry. Now I wanted to share this just to tell you kind of the process of how I like to study for this class, and then you kind of create yourself a plan right at the beginning and stick to it as you move through this class. Now this is a very fast-paced course, and there's a lot of material that's learned in a very short time. To ensure success in the understanding of this class, it's great to start the semester off with a plan. My personal plan includes the following. I want to read the chapter before watching any lecture videos. If I read the chapter beforehand, I already kind of have an idea about what's going to be taught. Then I can watch the lecture videos and maybe get my questions answered or make myself little notes to ask the teacher because I still don't understand this. Then I'm going to attend any class workshop that's held virtually. keep very clear and organized notes. Sometimes as I watch lecture videos, my notes get really messy because I'm trying to keep up with the material. So what I like to do is rewrite my notes after finishing the lecture videos to help keep them clear and organized. When I do have workshops with my classmates, I want to be an active participant, constantly asking questions and answering them and helping out my peers. I want to be good about attending office hours when they're being held and study as much as I can. Now, the best way to go about learning this material is to practice, reading ahead, looking over the videos, practicing the homework, going over all the practice problems of the lecture, and then redoing those as much as you need to in order to understand them. And with all those tools, you're in it to win it.